Mains electricity is the general-purpose alternating current electric power supply. In the U.S., electric power is referred to by several names including household power, household electricity, house current, powerline, domestic power, wall power, line power, AC power, city power, street power, and grid power. In many parts of Canada, it is called hydro, because much of the Canadian electrical generating capacity is hydroelectric. Mains power systems, for a list of voltages, frequencies, and wall plugs by country, see mains electricity by country. Worldwide, many different mains power systems are found for the operation of household and light commercial electrical appliances and lighting. The different systems are primarily characterized by their voltage, frequency, plugs and sockets, earthing system, protection against overcurrent damage, electric shock, and fire hazards, parameter tolerances, single-phase or three-phase power, direct current since the mid-20th century, but DC was the general rule in the past. All these parameters vary among regions. The voltages are generally in the range 100 to 240 V. The two commonly used frequencies are 50 and 60 Hz. Foreign enclaves, such as large industrial plants or overseas military bases, may have a different standard voltage and frequency from the surrounding areas. Some city areas may use standards different from that of the surrounding countryside. Regions in an effective state of anarchy may have no central electrical authority, with electric power provided by incompatible private sources. Many other combinations of voltage and utility frequency, including direct current, were formerly used, with frequencies between 25 Hz and 133 Hz and voltages from 100 to 250 V. The modern standard combinations of 230 V/50 Hz and 120 V/60 Hz did not apply in the first few decades of the 20th century and are still not universal. Industrial plants with three-phase power will have different, higher voltages installed for large equipment, but the common voltages listed here would still be found for lighting and portable equipment. Building wiring. In most countries, household power is single-phase electric power, with 2 or 3 wired contacts at each outlet. Neutral and line wires carry current and are defined as live parts. The line wire carries alternating current between the power grid and the household. The neutral wire completes the electrical circuit by also carrying alternating current between the power grid and the household. The neutral is connected to the ground, and therefore has nearly the same electrical potential as the earth. This prevents the power circuits from increasing beyond earth voltage, such as when they are struck by lightning or become otherwise charged. The earth wire or ground connects the chassis of equipment to earth ground as a protection against faults, such as if the insulation on a hot wire becomes damaged and the bare wire comes into contact with the metal chassis or case of the equipment. Mixed 230 V/400 V three-phase or 230 V single-phase based household wiring. Various earthing systems are used to ensure that the ground and neutral wires have the correct voltages, to prevent shocks when touching grounded objects. In some installations, there may be 2 line conductors which carry alternating currents in a 3-wire single-phase circuit. Small portable electrical equipment is connected to the power supply through flexible cables terminated in a plug, which is then inserted into a fixed receptacle. Larger household electrical equipment and industrial equipment may be permanently wired to the fixed wiring of the building. For example, in North American homes a window-mounted self-contained air conditioner unit would be connected to a wall plug, whereas the central air conditioning for a whole home would be permanently wired. Larger plug and socket combinations are used for industrial equipment carrying larger currents, higher voltages, or three-phase electric power. Circuit breakers and fuses are used to detect short circuits between the line and neutral wires, or the drawing of more current than the wires are rated to handle to prevent overheating and fire. These protective devices are usually mounted in a central panel in a building, but some wiring systems also provide an overcurrent protection device at the socket or within the plug. Residual current devices, also known as ground fault circuit interrupters and appliance leakage current interrupters, are used to detect ground faults, leakage of current to somewhere other than the neutral and line wires. When a ground fault is detected, the device quickly cuts off the circuit. In Northern and Central Europe, residential electrical supply is commonly 400 V three-phase electric power, which gives 230 V between phase and neutral. House wiring is a mix of three-phase and single-phase circuits. High-power appliances such as kitchen stoves and household power-heavy tools like log splitters are very often attached to 400 V three-phase power. Example of standard AC power wire colors: Australia, active, brown or red; neutral Euro blue or black; earth Euro green/yellow. Standard voltage difference between connector, active, neutral 230 V to 240 V, active, earth, 230 V to 240 V, earth neutral OV to 1.5 V. A Eurocent ideal voltage difference between earth and neutral is 0 V, as neutral is connected to earth at the main power panel to prevent electrocution. A Eurocent practical voltage difference between earth and neutral is 0.1 V to 1.5 V as per the impedance difference between earth wire and neutral wire. A Eurocent ground wire has a much lower electrical resistance than neutral wire, which results in a difference of electrical potential between them. Earth and neutral. Example size of earth cable: a 4 mm electric cable. 4 mm size cable can be used to electric oven. Cable size for power points are 2.5 mm, light 1.5 mm. Voltage levels: most of Europe, Africa, Asia, Australia, New Zealand and most of South America use a supply that is within 6% of 230 V. In the UK, Australia and New Zealand the nominal supply voltage is 230-6% plus 10% to accommodate the fact that most supplies are in fact still 240 V. Japan, Taiwan, North America and some parts of Northern South America use a voltage between 100 and 127 V. The 230 V standard has become widespread, so the 230 V equipment can be used in most parts of the world with the aid of an adapter or a change to the equipment's connection plug for the specific country. Measuring voltage: a distinction should be made between the voltage at the point of supply and the voltage rating of the equipment. Typically the utilization voltage is 3% to 5% lower than the nominal system voltage. For example, a nominal 208 V supply system will be connected to motors with 200 V on their nameplates. This allows for the voltage drop between equipment and supply. Voltages in this article of a nominal supply voltages, and equipment used on these systems will carry slightly lower nameplate voltages. Power distribution system voltage is nearly sinusoidal in nature. Voltages are expressed as root mean square voltage. Voltage tolerances are for steady-state operation. Momentary heavy loads, or switching operations in the power distribution network, may cause short-term deviations out of the tolerance band. In general, power supplies derived from large networks with many sources are more stable than those supplied to an isolated community with perhaps only a single generator. Choice of voltage. The choice of utilization voltage is due more to historical reasons than optimization of the distribution system. Once a voltage is in use and equipment using this voltage is widespread, changing voltage is a drastic and expensive measure. A 230 V distribution system will use less conductor material than a 120 V system to deliver a given amount of power because the current, and consequently the resistive loss, is lower. While large heating appliances can use smaller conductors at 230 V for the same output rating, few household appliances use anything like the full capacity of the outlet to which they are connected. Minimum wire size for handheld or portable equipment is usually restricted by the mechanical strength of the conductors. Electrical appliances are used extensively in homes in both 230 V and 120 V system countries. National electrical codes prescribe wiring methods intended to minimize the risk of electric shock and fire. Many areas such as the USA, which use 120 V, make use of three-wire, single-phase 240 V systems to supply large appliances. In this system a 240 V supply comes with a center tap neutral to give two 120 V supplies, which can also supply 240 V to loads connected between the two line wires. Three-phase systems can be connected to give various combinations of voltage, suitable for use by different classes of equipment. where both single-phase and three-phase loads are served by an electrical system, the system may be labeled with both voltages such as 120/208 or 230/400 V, to show the line-to-neutral voltage and the line-to-line voltage. Large loads are connected for the higher voltage. Other three-phase voltages, up to 830 volts, are occasionally used for special-purpose systems such as oil well pumps. Large industrial motors may operate on medium voltage. On 60 Hz systems, a standard for medium voltage equipment is 2300/4160 V, whereas 3300 V is the common standard for 50 Hz systems. Standardization. Following voltage harmonization, electricity supplies within the European Union are now nominally 230 VA plus or minus 10% at 50 Hz. For a transition period, countries that had previously used 220 V changed to a narrow or asymmetric tolerance range of 230 V plus 6% to 10%, and those that had previously used 240 V changed to 230 V plus 10% to 6%. No change in voltage is required by either system, as both 220 V and 240 V fall within the lower 230 V tolerance bands. Some areas of the UK still have 250 volts for legacy reasons, but these also fall within the 10% tolerance band of 230 volts. In practice, this allows countries to continue to supply the same voltage, at least until existing supply transformers are replaced. Equipment used in these countries is designed to accept any voltage within the specified range. In the United States and Canada, national standards specify that the nominal voltage at the source should be 120 V and allow a range of 114 to 126 V. Historically, 110, 115 and 117 volts have been used at different times and places in North America. Main power is sometimes spoken of as 110. However, 120 is the nominal voltage. In 2000, Australia converted to 230 V as the nominal standard with a tolerance of plus 10% to 6%, this superseding the old 240 V standard. American Samoa, 2926-1987. As in the UK, 240 V is within the allowable limits and 240 volt is a synonym for mains in Australian and British English. In Japan, the electrical power supply to households is at 100 V. Eastern and northern parts of Honshu and Hokkaido have a frequency of 50 Hz, whereas western Honshu, Shikoku, Kyushu, and Okinawa operate at 60 Hz. The boundary between the two regions contains 4 back-to-back high-voltage direct current substations which interconnect the power between the two grid systems. These are Shinchinano, Sakuma Dam, Minami Fukumitsu, and the Higashi Shimizu frequency converter. To accommodate the difference, frequency-sensitive appliances marketed in Japan can often be switched between the two frequencies. History of voltage and frequency. The system of three-phase alternating current electrical generation, transmission, and distribution was developed in the 19th century by Nikola Tesla, George Westinghouse and others. Thomas Edison developed direct current systems at 110 V, and this was claimed to be safer in the battles between proponents of AC and DC supply systems. Later metal filament lamps became feasible. In 1899, the Berliner Elektrische Current-CTS-Werke, a Berlin electrical utility, decided to greatly increase its distribution capacity by switching to 220-volt nominal distribution, taking advantage of the higher voltage capability of metal filament lamps. The company was able to offset the cost of converting the customer's equipment by the resulting saving in distribution conductors cost. This became the model for electrical distribution in Germany and the rest of Europe, and the 220-volt system became common. North American practice remained with voltages near 110 volts for lamps. In 1883, Edison patented a 3-wire distribution system to allow DC generation plants to serve a wider radius of customers. This saved on copper costs since lamps were connected in series on a 220-volt system, with a neutral conductor connected between to carry any unbalance between the two sub-circuits. This was later adapted to AC circuits. Most lighting and small appliances ran on 120 V, while big appliances could be connected to 240 V. This system saved copper and was backward compatible with existing appliances. Also, the original plugs could be used with the revised system. At the end of the 19th century, Westinghouse in the US decided on 60 Hz and AEG in Germany decided on 50 Hz, eventually leading to the world being mostly divided into two frequency camps. Most 60 Hz systems are nominally 120 volts and most 50 Hz nominally 230 volts. Voltage regulation: to maintain the voltage at the customer's service within the acceptable range, electrical distribution utilities use regulating equipment at electrical substations or along the distribution line. At a substation, the step-down transformer will have an automatic on-load tap changer, allowing the ratio between transmission voltage and distribution voltage to be adjusted in steps. For long rural distribution circuits, automatic voltage regulators may be mounted on poles of the distribution line. These are auto-transformers again with on-load tape changers to adjust the ratio depending on the observed voltage changes. At each customer's service, the step-down transformer has up to 5 taps to allow some range of adjustment, usually a plus or minus 5% of the nominal voltage. Since these taps are not automatically controlled, they are used only to adjust the long-term average voltage at the service and not to regulate the voltage seen by the utility customer. Power quality. The stability of the voltage and frequency supplied to customers varies among countries and regions. Power quality is a term describing the degree of deviation from the nominal supply voltage and frequency. Short-term surges and dropouts affect sensitive electronic equipment such as computers. Longer-term outages, brownouts and blackouts and low reliability of supply generally increase costs to customers, who may have to invest in uninterruptible power supply or standby generator sets to provide power when the utility supply is unavailable or unusable. Erratic power supply may be a severe economic handicap to businesses who rely on electrical machinery, illumination, and climate control. Even the best commercial quality power system may have breakdowns. See also: AC power plugs and sockets, domestic AC power plugs and sockets, electricity, energy meter, mains electricity by country, meter point administration number, three-phase electric power, voltage. References. External links: Grid monitor tools, real-time data from ERCOT.